we have to start this session exactly at 4 o'clock. And next speaker is Professor Chi-wang Shu from Brown University. And he's, just read what I'm talking to read. His background in numerical analysis and scientific computing, just the same as the session title. And Professor Shu got his bachelor degree from University of Science and Technology in China in 1982. And then he went to state and got his PhD at the University of California in Los Angeles in 1986 under Professor Stanley. And Professor Shu got many awards. The early ones are from NASA Public Service Group Achievement Award for pioneer work in computational fluid dynamics, and in 1992. Then he got Feng Prize, the first Feng Prize of scientific computing from Chinese Academy of Science in 1995. Then he has been a highly cited author in mathematics from ISI Web of Knowledge from 2004 until today. Keep that record. And then 2007, he got assigned ICM Prize in Computational Science and Engineering. Then 2009 and also 2012 is an inaugural fellow, the first batch from SCIEM, okay, Society for Industrial and Applied Mathematics, and also the fellow for American Math Society in 2012. This is the first group of fellows. And the title of his talk is Discontinuous Galerkin Method for Time-Dependent Convection-Dominated Partial Differential Equation. Please.
Okay, thank you very much. I will talk about a class of numerical methods for solving time-dependent convection-dominated PDEs, mainly hyperbolic problems and other problems for which the hyperbolic class dominates. So this is an outline of my talk. We have DG method. We'll start with DG method for hyperbolic conservation laws, and then move on to convection diffusion equations where convection dominates, convection dominated partial differential equations of higher order, third and higher, and then we will give some concluding remarks. Okay, so let's start from DG method for hyperbolic conservation laws. So this is the equation. Historically, the DG method was designed for exactly solving such kind of equations. In 1D, it looks like this. F here is a nonlinear function of u, and u here could be a scalar or a vector. If it is a vector, f prime of u is the so-called Jacobian, and it's assumed to be diagonalizable with real eigenvalues. So that's the definition of hyperbolicity. In 2D, it looks like this, with one more nonlinear flux, Gu. First of all, why would there be any interest and difficulty in solving such problems numerically? The foremost difficulty comes from the fact that the solution U may become discontinuous, and this is generic. It's regardless of how you put the initial and boundary conditions. So you could start from initial condition, which is very, very smooth. Still, the solution may become discontinuous in finite time. So this poses difficulty in designing good numerical methods. Mathematically, there are problems also. For example, you have to define weak solutions, and weak solutions may not be unique. So in order to single out a unique, physically relevant weak solution, you need to add an extra condition which comes from physics, called entropy condition. Mathematically speaking, this is the inequality you need to satisfy for a convex scalar function. You remember the small u could be a vector, but capital U is a scalar function. And we assume capital U is convex, which means capital U double prime is positive. It's a positive matrix. And then F here is a consistent entropy flux. So this inequality should be satisfied in order to single out a unique physically relevant solution. Okay, now let's come to the description of the DG method. Again, we use this one-dimensional case to set the ideas. So we have ut plus fux equals 0. Let's, in 1D, right, let's set a discretization which consists of just several intervals, xj minus half to xj plus half for j running from, let's say, 1 to capital N. We multiply this equality by a text function v, and we integrate over this cell. So the only thing we do on top of that is to integrate by parts for the second term. Fux times v is integrated by parts to generate fu times vx plus 2 boundary terms, interface terms, at the cell boundary ij. Notice that this is an equality satisfied by the exact solution of u multiplied by any C1 function, C1 test function v. So this is an equality. It's not a scheme, it's a property satisfied by the exact solution of the PDE. Now the idea is to convert this to a scheme. So what do? Well, you first pick a finite dimensional function space. The most commonly used one would be piecewise polynomials of degree k here, which means it is a polynomial of degree k in each cell ij, but across different cells at the cell boundary does not have to be continuous. So you collect all such functions, you call it VH. Then you would want the previous equality to be satisfied by some function u in this space VH, and the test function v, which is also from this same VH, hence Galerkin. Now, the problem, of course, is that the previous equality has those interface terms, and if you consider u and v to be both from the space VH, then these terms are ambiguous. They are not uniquely defined. Because u here at j plus half could have a left limit, could have a right limit, and they could be different because you allow these continuities at the cell interface. So this certainly poses, you can say poses difficulties, but you could also say gives you opportunities, right? So you view it in an optimistic way. So this is actually an opportunity. So you define those interface terms in a suitable way, you end up with a good DG scheme. So the whole thing about DG would be how do you handle these terms. Okay, so how do you handle them? Well, for u, you have this ambiguous term f of uj plus half. You replace it by a so-called numerical flux f hat, which the physical flux f is a function of one variable u only, but the numerical flux is a function of two variables, u minus and u plus, taking into consideration that the function from the left and from the right have two different limits. So you have u minus and u plus. F hat is a function of these two guys, and it satisfies certain conditions. The most important condition is this one. It's increasing the first argument, decreasing the second argument. Remember, this is the scalar case. So this is called monotonicity, and good properties, good mathematical properties come from this monotonicity assumption, which implies monotonicity for the first order scheme, convergence, and so on. So also it has to be consistent and Lipschitz continuous. So this is for u. And this idea is not coming from DG. This was an idea already explored by finite volume and the finite difference schemes before DG. So this was a technique borrowed from the finite volume and the finite difference technology. Here, the test function v is simple. You just take it from inside the computational cell ij. So on the right boundary, you take it from the minus. On the right boundary, you take it from the plus. So with that, you have equality 1 becomes equality 2, which means this equality for which f is replaced by f hat, v is replaced by values from inside ij, then this equality is supposed to be satisfied by every test function v in the space VH. You can show that there is only one function u in the space which satisfies this, and that is your numerical solution. Of course, in order to go to the computer to implement this scheme, you have to choose a local basis. You convert this to some scheme which looks very much like a finite difference, finite volume scheme. Can be very easily implemented. Okay, so in time you can do, so this is what I have been talking about is a spatial discretization. In time, you simply use a Runge-Kutta method, for example. For example, the TVD type Runge-Kutta method in this paper. Now, this method, very simple minded method, has many unique and good properties. For example, it's very easy to handle geometry and boundary conditions in the finite element method. You can see that the design of the method relies on integration by parts, which in multi-D would just be Green's formula divergence theorem. So you can easily do it on general geometry and general boundary conditions. Also, because of discontinuity, you can also allow hanging nodes. This is a property very closely related to the fact that the space could be discontinuous. This method is very compact. If you write it down, you will find out that in order to evolve the solution from time level n to time level n plus 1, you only need the information of your local cell and your two immediate neighbors. So this is a very compact scheme, regardless of the order of the scheme. So this is actually quoted as an advantage over finite difference and finite volume schemes of high order. Because finite difference and finite volume schemes, if you want high order accuracy, you need a wider and wider stencil to do an interpolation or reconstruction using information from many faraway neighbors in order to build a high order accuracy. Here you don't. This is an explicit method, and hence, because of the two previous facts, the parallel efficiency of the method is excellent. So you get basically 100% parallel efficiency if your mesh does not change over time. Even if it does change, you still have very reasonable parallel efficiency. And more recently, people have been exploring this method on GPU architecture. Again, it is very suitable for GPU architecture. Okay, now theoretical properties of the method. First of all, there is a very attractive property that the method satisfies a discrete version of the entropy inequality I mentioned before, which is useful for single unique solutions. So you have a discrete version of the entropy inequality for the numerical solution U. So here, this is U here. I am using notations. This U now is the numerical solution. You have exactly the same inequality that you required before for the square entropy. Because of this, you also, if you sum over J, you basically get L2 boundedness, which is a very nice property. So your solution will not blow up in L2. And this is true, of course, for the semi-discrete version, but also it is true, at least for linear equations, for the fully discrete version. The scheme. So this is the stability. The stability is valid whenever your solution is a weak solution to the PDE. So approximating a weak solution to the PDE, you don't need smoothness. So that's a good part. If, on top of that, you know that your solution is smooth, for example, your solution has k plus 1 derivatives, then you have the so-called error estimates. Your solution, UH minus U, is high order accurate, high order close to the exact solution U. It's either at least k plus half order and often k plus 1 order for polynomial degree k. So this is considered optimal. And this has a long history of proof for such error estimates. Starts from the very early work of Lassonde and Rabiat, and then continuing to, you can see here some preprints that continuing for different cases with stronger results, stronger and stronger results with lesser and lesser assumptions for DG schemes. So this is still an active research area. So this is for smooth solutions. This again is for smooth solutions, so you have the so-called superconvergence, which means if a Galerkin method, even if you are using polynomial degree k, you can get accuracy of 2k plus 1. It's too good to be true, but it's actually true. For example, piecewise linear, you can get third order, piecewise quadratic, you can get fifth order, and so on. Of course, these kind of error estimates are in very special negative norms. And after post-processing, you can also realize it in strong L2 norm. So this series of work starts from the paper by Cockburn, Laskin, Sully, and myself in about 10 years ago, and then a lot of follow-up works along this direction. Okay, so this is one type of superconvergence. The other type of superconvergence is to say that you don't post-process, you don't look at the weak norm, you look at the strong norm, but then you will not have that kind of very high order superconvergence. You still have at least one order higher when you measure it in certain way. For example, if you look at the solution at certain special quadrature points, they are superconvergent. If you look at the numerical solution minus not the exact solution, but the special projection of the exact solution, you have superconvergence. So you might say this is a mathematical game. What is the use of it? Actually, it's not. It actually explains a very interesting phenomenon observed by engineers, that if you use DG method, you use it to compute wave equations. You run it for a very long time. The errors do not seem to grow with time. For example, after one time step, the error is 10 to the minus 2. After 1,000 time steps, it is still 10 to the minus 2. That defeats our intuition of finite difference, right? Usually you say finite difference, the error grows linearly in time, accumulates linearly in time. That's already very good, but this one doesn't change over time. Of course, it's not really true. It does change. However, it stays constant for a very long time on this level, which means if you look at reasonable time horizon, your error seems to be constant in time. So this theory explains this observation made by engineers. So very nice. This part also is recent work. It's important because what I've been mentioning before, of course, I was assuming the solution is smooth, but I already told you that the solution to the hyperbolic problems are in general not smooth. They may have discontinuities. So what happens if your solution is discontinuous? What can you prove? Well, much less, unfortunately. But you can still prove something. For example, you can prove optimal L2 error estimates of DG for discontinuous solutions in a region away from the discontinuity. How much away? Well, basically all the square root h away from discontinuity. So if you exclude a region of square root of h, then you can prove. You observe this numerically, of course, but this you can also prove, at least for linear problems, that this is true. So you get the optimal L2 error estimates. Okay, now this is also a sequence of recent work, which was also mentioned in the previous talk, that the non-oscillatory property of the scheme is important, but it cannot be satisfied by the original DG scheme or any scheme because of the Gordonov theorem. Gordonov theorem says that if you have a linear scheme, which means a scheme which is linear when you use it on linear equations, then it is either oscillatory or it is only first order accurate. You just pick one of them. So if you want a high order scheme, it must be oscillatory if it is a linear scheme. So you would have to put some nonlinear limiters in order to obtain non-oscillatory performance while keeping high order accuracy. Now, amazingly, you could actually do this for DG schemes, even for systems, for scalar equations for systems, without killing accuracy. So this seems too good to be true. So, but you can do that. Actually, you can design a bound-preserving limiter, which applies to the DG solution as a post-processor, which amazingly keeps order of accuracy even at extrema, doesn't kill accuracy, and it gives you bound-preserving properties. For example, for scalar equations, you have local Mason principle, and for systems, you have positivity for the quantities which should be positive. For example, density and pressure for Euler equations. So again, this is a sequence of recent work in this direction. Okay, so this is one type of limiter, bound preserving. The other type of limiter is to control oscillations. Bound preserving doesn't control oscillations. It just controls that you don't go out to the place where you shouldn't be there. For example, if it is some percentage, it should stay between 0 and 1, and bound preserving means you're not going to go beyond 1 or below 0. However, if you are at 0.5, then you could still be oscillatory if you apply a bound preserving limiter. In order to control these oscillations, you need some kind of stronger limiter, which unfortunately, again, it's a difficult issue. So how do you design a limiter which is easy to use, which controls oscillations, which does not kill accuracy, or at least not kill accuracy so much, and so on. So it's a very difficult topic. It's still a research area. And for example, here I mentioned in particular these Wiener type limiters, which have been constructed recently in the literature. For example, Zhong and myself, JCP13, this paper, Zhu and Zhong and Chu and myself, JCP13, that seems to be a limiter that have a lot of good properties. So local does not kill the property of DG of local stencil, uses only neighboring cells, keeps the order of accuracy, and relatively easy to construct. The method, DG method, is easy for HP adaptivity, which means you can locally refine the mesh, or you can locally increase the polynomial of degree, or both. And again, as I mentioned, that DG method not only have been designed for hyperbolic conservation laws, but they could also be designed for other PDEs containing higher order derivatives, which is what I would continue to describe. Here is a pretty incomplete history of DG methods. The first DG paper appeared in 1973 as a Los Alamos technical report. So almost every DG paper refers to this paper as a very highly cited paper, but it's not in SCI, right? It's a technical report. And then immediately after that, the French school picked it up and proved that the method is nice. You have stability and error estimates. And then there's a sequence of work by the group of Johnson, this is Klaus Johnson in Sweden, that proves the error estimates for this type of DG methods. But these type of DG methods are designed for being used on linear problems. They basically follow characteristics, so they are very easy to use. If you know the characteristics for linear problem, you do know. You know where is your upwind side, your downwind side, but they are very difficult to use for nonlinear problems because the upwind side depends on the solution, so you don't know it beforehand. And so later, Cobb and myself, we worked on a way to overcome this difficulty of nonlinearity. Well, to put it simply, we basically do the DG only in space, and we forward in time by Runge-Kutta. So this way, at time level n, certainly I know the solution, hence I know the upwind direction. So that's all. So then you can use it, you can get better flows. So you get this kind of so-called Runge-Kutta DG methods. And then you can design it for scalar equation systems, you can prove certain things and so on. For example, the cell entropy inequality I mentioned before. So if you want to look at the literature of DG, so here I listed some of them, conference proceedings, special journal, special issues, and also books. So at least there are many, many books in recent years on DG. For example, this is a more engineering book, and there are books here that you can look into if you want to know DG methods. Okay, so let's move on now to some examples, just to show you that how it works, right? So this is a linear equation, of course, but I ran it for a very long time. Ran it to t equals 100 pi, which means this solution turns around 50 times. On a relatively coarse mesh, which is basically 40 cells, I think 40 cells. So for P1, you get this solution, which is pretty smeared, but still reasonably shaped. For P6, which is 7 orders DG, you basically get the exact solution in a very good shape. There is still some oscillations because limiters are not used in this computation. This is also true in 2D. Now the next example is variable coefficient. So variable coefficient, so you can do amazing things. Basically, you design so that the exact solution at the beginning, the level set is a straight line, and then it gets turned around more. So here you're actually looking at two. They look at only one curve, but there are actually two curves. One is the exact solution, the other, these dots are the DG solution, piecewise polynomial of degree 4, with not so refined measure, 24 by 24. And this thing turns around so many times, you can still see that the exact solution and the numerical solution are on top of each other. Very amazing. And here it turns more. Still, the resolution is very good. And then it unwinds. So you design the coefficient so that it turns around. Then it unwinds, comes back to the initial flat line, and see the numerical solution also comes back to the straight line. So very few other numerical methods can do this on such a coarse mesh with such a long time. So this is indicating the good wave resolution property of DG methods. And this is nonlinear double mark reflection. You can see that you compute the solution, especially near the region here. So the top is P2, the bottom is P1, but the P2 uses only half of the points in each direction than the P1 cells. And you can see that they get similar performance. And final numerical result is for an equation. It looks like a conservation law, but the flux depends on, it's not a local function. So this one has a very interesting property that even if the initial condition is bounded, smooth, later when t goes to infinity, the solution becomes unbounded, becomes a bunch of data functions. So this is also very difficult to simulate because it's not just discontinuous, it blows up. And then if you use the usual limiter, it will seriously affect the resolution because the usual limiter limits the slope. And for data functions, you really want the slope to be sharp. So this is a difficult thing to simulate. But the DG with the bound preserving limiter, with no other limiters, you shouldn't use the slope limiters. You can compute this thing with very nice results. So this is a computation. You can see these are data functions. And this is a P0, this is a P1. We argue that P1 is better because there's a conservation. The area underneath these guys is the same, it's conserved. So the taller these data functions, the narrower they are, right? Because the area will be the same. So the P1 result resolves the data function better than the P0 results. Okay, there's another one. So this is pressureless Euler equations. Again, it can generate data functions in its solution. And with the bound preserving limiter, the DG, you can compute these kind of solutions in a very nice way. So for example, solution becomes a data function in the middle, and you can compute it very nicely. The solution becomes a data function plus this is a zero-dimensional data function, this is a one-dimensional data function. This is the exact, we know the exact solution of this problem, and the DG solution recovers that very nicely. Again, this is the data function on the screen. This is the velocity. Basically, the velocity is going out from inside, going in from outside, pushing everything to this circle, becomes a data function. Again, the DG method with the bound preserving limiter can compute this in a very nice way. Okay, so this is for hyperbolic problems. Now, for a convection diffusion equations, for example, just the Hill equation, what do you do? Well, the previous, I described the methodology based on conservation law. You might say, well, this is not a big deal because this is a conservation law, right? You just say, take Fu, replace Fu by minus Ux. Then it becomes Ut plus parenthesis minus ux sub x equals 0. So in the previous DG scheme, everywhere you see fu, you replace it by minus ux. It should do the job. But actually, if you do it that way, you write down this scheme. Of course, you still need to put the numerical flux somehow. Remember that before we were using the so-called monotone scheme, we were using upwinding principles to pick the flux. Right now, of course, for heat equation, there is no wind, preferred wind direction. So one possibility would be just take the average. So you average them up, right? And put it in here, go to the computer and compute. This actually does not give you good results. So this is what you get. You refine the mesh, the error doesn't decay. You see the error stays basically as constant when you refine the mesh. And you look at the solution, basically the symbols are the numerical solution, but the solid line is the exact solution. The solid line here is the exact solution. Symbols represent the numerical solution. So they do not converge, right? Numerical solution do not converge to the exact solution, but they converge to themselves. But if you refine the mesh, they stay at the symbols. So this is a disaster, right? So if you have a scheme which looks stable on you, but computes something which is wrong, certainly that's the worst you want to see. So that means you really have to be careful when you design DG methods for equations other than hyperbolic. So we have some analysis in this early paper on what happens here. To fix that, there are many ways to fix this. One possible way is to introduce auxiliary variables and design DG schemes on this equation. So you call Q to be Ux, and you weakly solve, you write DG schemes for these first order derivatives, just like in conservation laws, you write them here, and you choose those numerical fluxes in a way which gives you stability. So for example, you can choose them in this alternating fashion, which would work. Then you have results, which are methods which will be L2 stable and optimal convergent. And it works also for the nonlinear case. So this is one way, but there are many other ways. Okay. Many other ways you can handle this convection diffusion equation. I want to emphasize that the reason that you want to use DG method for the diffusion equation, at least for my purpose, is that you want to solve convection-dominated convection diffusion equations. For example, Navier-Stokes equations with high Reynolds numbers. You want to stay within the DG framework to handle the second derivative. I probably would not use it, at least for my purpose, on diffusion-dominated Navier-Stokes equations, low Reynolds number Navier-Stokes, unless there's another purpose, for example, adaptivity and so on. Otherwise, any other continuous finite elements will do. So, but for convection-dominated problems, I would want to utilize the very good performance of DG methods for shocks, for hyperbolic component, so that I will be able to get good results with reasonable mesh. Okay, so here you can see that with this fixed LDG methods are high order, and you can get you can also get super convergence. You can get Larson principle. So the things you have done for the hyperbolic case can be, in general, generalized to convection diffusion. For example, if you look at this thing, this equation, this m is a number bigger than 1, you can see that the solution without the bound preserving limiter could go underneath 0, which is dangerous because the previous nonlinear equation, this nonlinear equation, if u becomes negative, this is not even well posed. So it's an ill-posed PDE. So you really want to control the solution. You don't want this kind of thing. Of course, this is a zoom. If you don't zoom, you don't really see it too much. But still, with the bound preserving limiter, you get very nice results. Okay, the same thing can be done for higher order PDEs. So higher means higher than 2. So for example, for third order PDE, KDV equation, you can do the same thing. What you do is that you introduce 2 auxiliary variables. You have Q equals to Ux. You also have P equals to Qx, which means P equals to Uxx. Then you repeat what you have done before. You have 3 equations, you have 3 fluxes. This is 3 DG scheme. And then you compute, you take these fluxes in an alternating plus upwinding wave. All the wave equations, first order equation, third order equation, fifth order equation, these are wave equations. They have a preferred wind direction. So your middle guy is always picked according to upwinding of that wind direction, and the remaining ones are alternating. So this is the principle you could use in designing the numerical fluxes. Then you have good results, you have high order accuracy. You can also prove all these nice properties of true stability, optimal error estimate, superconvergence, and so on. Okay, so for example, you can see that computing this, I apologize for this picture, but you can probably see that it's a quite oscillatory thing, and you can compute the solution with DG very nicely. This is not numerical oscillation, this is the dispersive KdV equation, which the solution itself is oscillatory. You can see that with smaller and smaller epsilon, you can get more and more oscillations where the DG scheme can still compute them nicely. You can generalize this type of methods to many different nonlinear PDEs from mathematical physics and other applications of containing higher order derivatives. For example, the so-called KMN equation, fifth order KdV, KNN equation, Schrödinger equation, Hamasa-Holm, many different equations. So basically the idea is that if you have a nonlinear PDE coming from applications with a good energy, so it's a nonlinear function of the solution, which is positive, it does not increase with time, it's energy, some kind of energy. Then you design a DG scheme to satisfy the same energy estimate. Then that will be your starting point. You get a good scheme, you can estimate then the convergence. You can also do the same thing for diffusive equations. This will be the second order, fourth order, sixth order, and so on. So previously I was talking about the dispersive wave equations. Here they are not waves, they are diffusive equations. You can also do the same thing in design methods, which can be designed for such diffusive equations. Okay, now let me give some concluding remarks. Discontinuous Galerkin methods are very flexible to geometry, boundary condition, and HP adaptivity that explains their popularity in recent years in applications. Stable and accurate DG methods have been designed for many PDEs, starting from conservation laws, going all the way to convection-dominated convection diffusion equations and the convection dispersion equations. But there are still a lot of open issues to be done in order to utilize DG methods better. For example, more nonlinear PDEs, efficient time discretization, which I basically did not mention in this talk. So how do you discretize time in a more efficient way? For hyperbolic equations, you can use Roche-Coulton explicit, but for other equations, you better use something else in order to gain efficiency. And also, another thing which mathematics can help is that this method is very flexible for adaptivity. It's flexible for both H and P adaptivity. However, in order to do this in an effective way, you have to have mathematics to back you up, to tell you where you should refine or where you should increase P, right? Otherwise, even if you have this capability, you do not know where you should refine to get good results. So here, I would say mathematics can play a crucial role. You have a good, very reliable posterior error estimate that could guide your adaptivity. So with that, I will finish my talk and welcome questions.
Okay, any questions?
Can you tell us some more about posterior error estimate for this scheme, please?
Right, yeah, so the most difficult one would be for hyperbolic equations. Yeah, so right now the idea is still using adjoint approach, which has practical limitations because, for example, for time-dependent problems, you would have to first solve the equation upward in time, store all the intermediate results, and solve the adjoint problem backward in time. So this is computationally very intensive. So yeah, so this is a difficult thing. But on the other hand, this has to be done because in order to really utilize the power of DG method, somehow this has to be done.
So for the PPA equation with small parameter epsilon, you show epsilon small, the wave length becomes smaller. So when you're using DG, your mesh size depend on epsilon or not?
It does. It does, right. So the method is stable doesn't mean it can resolve those kind of waves with cost mesh.
So one more time, you're happy with your limiters these days? Or?
I'm not happy. So that's why it's always trying to improve the limiters. So the most recent one is the closest that we are close to our happiness, which is a very local limiter using only immediate neighbors and reasonably easy to construct using Wayne-Node technology.
So conceptually, though, this is still like ENO, except instead of a polynomial basis, you use these discontinuous polynomial approximating spaces. Right?
Yeah, but it doesn't have, well, the one without the limiter doesn't have this ENO component. It's a linear method. You would rather say it's a fixed stencil thing. It's just that stencil is narrow, it's just one cell.
Can you characterize the stability limit time on delta D, say, in terms of the order of the rugged data and of the order of the spatial parameterization?
Yes, so this is, so for explicit time discretization, it basically goes like 1/2k plus 1, which is very severe, which means you use polynomial degree k, your CFL scales like 1/2k plus 1. There are some variants of DG methods which could be better. For example, those so-called staggered DG, central DG, which looks more like 1/k rather than 1/2k. But still, this is a limitation, so that's why I was mentioning at the end, efficient time discretization would be an issue.
Is this dependent the same for every rugged data order?
Yeah, yeah. There's no good logical.
So is there room for pure ENO left in this world, or is that?
Excuse me?
Good old ENO, is that?
Good old ENO is still there. Because this thing is good for unstructured mesh, for adaptivity. But if you have a rectangular mesh, the good old ENO is still 10 times faster than this. So.
Okay. You should say that.
For the super conversion, do you have any explanation for that?
Excuse me?
For the super conversions,
Yes.
do you have any explanations?
Why you have superconvergence? Yeah, because it's a Galerkin method. Yeah, usually Galerkin method contains hidden information that allows you to double the order of accuracy.
Yeah, other questions? Okay. Now let's, on behalf of the local organizing committee, you get a small souvenir.
Okay.